Hey, Dr. Clark here, and in this preview video, we're going to be looking at properties of the Laplace transform. Let's take a look. So first, just remember just some of the basic Laplace transforms we've seen already. L of 1 is the 1 over s, L of e to the t is 1 over s minus a, and then you got sine and cosine functions landing on their particular things, and etc. Right? So again, the idea was we're converting functions of time into a function of s, and sort of the idea is s is kind of like a frequency, if you will, in the sense of, but in the sense of e to the t. So it's kind of picking out how can you take an input function and characterize it in terms of e to the t in some way, right? Okay. And one of the things I want to talk about is sort of the spike in the Laplace transform. That spike tells you information about the given function. So if we start with just the one function, we see that the spike in 1 over s occurs at 0, and that's because the one function is really e to the 0t is 1. So the frequency that is highlighted is at 0. Okay, now what I want to know is what is the effect of multiplying by e to the at on the Laplace transform. So if I start with the function, say the one function, and I multiply that function by e to the at and then take the Laplace transform, what happens? Okay, so let's just take a look at it here. Let's say I multiply by e to the 2t, for example. Okay, well, on the one hand, if the original y function is 1, then e to the 2t times 1 is really just e to the 2t, and the Laplace transform of that is 1 over s minus 2. And so the spike shifts from 0 over to 2. Okay? So multiplication by e to the 2t in the time space has the effect of shifting the graph by 2 units in the frequency space. So it's still sort of the 1 over s graph, but it's been shifted over 2 units. You can think of it as basically replacing s with s minus 2. Okay, and you can see kind of how that works if you actually do the definition of the Laplace transform. You're going to get y of t, but you're going to be multiplied by e to the 2 minus st if you sort of multiply these together. And there's going to be a change of variables and some technical details, but there's going to basically be a shift of s to s minus 2, essentially, is what's going on there. Okay, and it turns out that this isn't only true when y of t is the one function. It's true in general. For example, take cosine or sine. So remember the Laplace transform of the sine function, sine of wt is w over s squared plus w squared. Well, what would happen if we'd multiply sine by e to the at in the time domain? Well, what's going to happen is you're going to do that same shift of s being replaced by s minus a. So it takes that spike and slides it over a units, and so there's a translation in the frequency domain. And same thing would go for cosine. S would be replaced with s minus a. S is replaced with s minus a. So it's a general principle of multiplication by e to the t in the time domain leads to a shift by s to s minus a in the frequency domain. Okay, you can write that more technically using the Laplace language. The Laplace of e to the at times f of t is really the regular Laplace transform of f, right? So if L of f is capital F, and then you just replace s with s minus a. Okay, so the Laplace transform of e to the at times f is the regular Laplace transform of f by itself, but with s replaced with s minus a, right? You can see here s is replaced with s minus a, s is replaced with s minus a. Okay, so multiplication becomes translation. Multiplication by e to the t turns into translation in the frequency domain. And similarly, the inverse would be if you had a translated function, it would come back as a product of e to the t and f. Okay, so now why do you care about this? It seems all very technical and nonsense. Well, it's going to be really important when we start solving differential equations this way, because some of the second order differential equations that we want to solve are going to have solutions that look like e to the t sine of t. And so when we look in the frequency domain of Laplace transforms, we're going to get things that look like s minus a over s minus a squared plus w squared, right? We're going to see things that look like s replaced with s minus a. And so when we translate back, well, we'll just get the sine function times e to the at or whatever it is, right? So that's going to be how we're going to end up using this. So more details to come, and we'll see you there.